8th International Physics Olympiad, year 1975, IPHO. I offer private tutoring for Physics Olympiad preparation. I currently have openings. Measure me if interested. My email is fred1996@hotmail.com or use Skype name Eduard F1996. Problem number 1. Rotating rod. A rod revolves with a constant angular velocity omega around the vertical axis A. The rod includes a fixed angle of pi over 2 minus alpha with the axis. A body of mass m can glide along the rod. The coefficient of friction is null, equal tangent beta. The angle beta is called friction angle. Question A. Determine the angles alpha under which the body remains at rest and under which the body is in motion if the rod is not rotating. It means omega equals 0. Question B. The rod rotates with a constant angular velocity omega greater than 0. The angle alpha does not change during rotation. Find the condition for the body to remain at rest relative to the rod. You can use the following relations. Solution for problem number 1. Let's check the first case A, when omega equals 0. In that case we have two equations for free body diagram. We suppose that our body is not moving. In that case, in a direction parallel to the slope, we have mg sine alpha equal force of friction, and perpendicular to the slope, mg cosine alpha equal normal force. In our case, force of friction must be less or equal to mu n. So it means that force of friction must be less or equal to mu mg cosine alpha, and we can combine these two equations to find this one, and finally that tangent alpha must be less or equal to mu, which is tangent of a critical angle beta. So for that case, this body is not moving. If tangent alpha greater than mu equal tangent beta, our body will move down, and this is the solution for question A. Solution for case B, when omega greater than 0. First, we suppose that this omega, or beta r omega square, very small. In that case, force of friction still going to the up and the right, and we can write the expressions for both forces like this. Now in our rotational frame of reference we have additional force mr omega square, which is going out of the center of rotation, and both equations have these expressions. Again, for critical force of friction F equal mu n. In that case we have these two equations, and now we can put expression for n here and use mu equal tangent beta. So we have this one. Now we can multiply everything by cosine beta, and we will get this formula. Now we can see that here we have sine alpha minus beta, and here we have cosine alpha minus beta. So we have this one. In case of critical angle we have this one. We can see that for small r and omega square, still for alpha less than beta, our body is not moving. but we can make angle alpha greater than beta, and for some relation between r omega square over g, we can exceed tangent alpha minus beta, this number. In that case, our body will go down. In this tangent less than this expression, it will not go anywhere. So that was a solution for small r omega square. Now let's check what happened in case B when r omega square big enough that force of friction F must go downhill to compensate ability for body to go up and right. So in that case we can rewrite our equations in form of this one, where force of friction F changed the sign. Now imagine that force of friction F has critical expression mu n. In that case we have this expression, and now we can put this n to the first formula, and instead of mu, again we can use tangent beta. So we have this expression. Now again we can multiply both parts by cosine beta, and we will get this one. And in this case we have for both parts expressions for function alpha plus beta. So we have this one and finally this one. Because this is the expression for critical angle, it means that if tangent alpha plus beta exceed this expression, our body is not moving anywhere. But if this tangent became less than this expression, the body starts to move up and right. So that was a full solution for problem number 1.